Okay, hi. So it's Monday, April 5th, Polymer Physics class. I wanted to, it's pre-recorded because I'm at the ACS meeting. So let's see. So I want to go through the quiz first. The quiz was on this paper by Chatterjee. Let's see. So Orski, I guess, sorry. And then it's with a group from NIST, National Institute of Standards in Gaithersburg, Maryland. Right. So they're looking at quantification of branching, short chain branching and low density polyethylene. So the problem is that they usually put in, they'll have an ethylene monomer and say an octene monomer. So you have like a six carbon, 3, 4, 5, 6. That'll be octene. Then there's also hexene. There's different. So they'll add these different monomers in, and then do like a radical polymerization. So you get a random sequence of ethylenes, and once in a while there'll be an octene branch on it. Right? So the way that works is that will limit the crystal thickness to the distance, kind of the average distance between octene branches, or actually maybe the shortest distance between octene branches. So basically that makes the melting point lower and it makes the crystallinity lower. So you have a lower crystallinity material when that happens. The melting temperature is going to go with the thickness of the crystal goes with the 2 sigma over delta H times the quench depth, right? Times T infinity and T minus T infinity. So the thinner the crystal, the deeper the quench depth. So you don't have a lower melting point, Tm here, for the crystal. This is for an infinite, T infinity is an infinite crystal melting point. That's the Hoffman-Lorentz equation. And Hoffman-Lorentz actually were at NIST, at the same place where this paper was made, but they were in the 1960s. And this is I think a 2020 paper. So the problem with this is that these placements are somewhat random, so it's not really a model system to look at. And so they wanted to, instead of using that, they used octene monomer. So cyclic octene. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Right, and one of these is a double bond, so that makes octene. This has got one double bond in it, and then it's got a substitute, and it'll be like either 1 carbon, either 0, so C0, C1, C2, C4. So C4 would have 4 carbons off C8, C10. So they did all these different series, and then they did metathesis polymerization, which is it's kind of switching partners for double bonds. So say you have this cyclic, you have another cyclic pulls up, the catalyst site is here, and then it will switch the partners. So partner A, B, C, D. So instead of AC, it goes AB. So it'll go A, B, and then C, CD match up, and then the double bond remains. So then you have this big cyclic that's 16. Then if you do that enough, you're going to get eventually a linear chain that's got every 8 carbons, it's got a side group on it. Exactly, right? And then it's got double bonds in it left from the metallocene. This is called metallocene polymerization. It's kind of swap the partners of the double bonds. And then anyway, you still have the double bonds in it. So this is similar to hydrogenation of polybutadiene to make linear polyethylene. So polybutadiene, it's like this polymer, and then when you polymerize it, it makes like the double bond is in the middle, and then so it goes like that. So that's like PVD rubber, and then polybutadiene, and then SBR is butadiene and styrene rubber, right? So it's basically that monomer goes to that. So you can make this anionically, so you can make that monodispersed, and then you can hydrogenate it. So hydrogenation of unsaturated bonds to make linear, that would make a model polyethylene, like a monodispersed polyethylene. And here they're making a model linear low density polyethylene. So you're going to hydrogenate this. Hydrogenating it involves a high temperature and a high pressure. So you need a pressure reactor at high temperature, and then use a catalyst, and you bubble hydrogen gas through, and it breaks the double bonds and hydrogenates it. So it becomes like a polyethylene, right? And then you have these regular branches on it. The problem with this, the high temperature, high pressure, is that polyethylene also has hydrogen abstraction problems. So you have this chain, this polyethylene chain. Oops, these H's can get lifted off, and then you're left with a free radical on the carbon. Right? When you have a free radical, it can find a double bond, it can react with it. That'll make a long chain branch if you have polymers. So we're starting with a polymer that has double bonds. So if you do a hydrogen abstraction, those can react, and then it can make like a three-way bond here, a four-way bond. So you can have like the carbon and like that. Or you could have another free radical. So two of these can combine, and that also makes a four-way bond. Right? Or you could have an abstraction from the methyl group at the end, and that would make a three-way bond. Right? So you're going to get branching. You could possibly get branching from this reaction. To avoid that, they dumped in a lot of stabilizer, antioxidant. Right? So toluene, tripropoxide toluene, I think is what they use. So it's like a free radical scavenger. So there's some side groups that protect this, and this thing can pick up a free radical, and then it's protected by these side groups. I think it's TPT or something, tripropoxide toluene or something like that, or DPT. Right, there's a common antioxidant for this. So they put a bunch of that in and tried to stabilize it. But right, so then once they had that, then they did measurements of intrinsic viscosity, and they found out that so here's the octene with the side groups. Then when they synthesize, they end up with a double bond in the backbone that they hydrogenate at 140C, and they don't give the pressure here. They give ergonox is the antioxidant, so they're dumping a load of that in to try to prevent this abstraction problem, branching. So then they do IR, so they can count the methyl groups from the IR pattern. I mean, there's a peak for the methyl groups. I'm not sure they show it here. So they identify the methyl groups, and the methyls are only at the ends of the chain and at the ends of these branches. Right, so there's only a few ends of chain, so they can forget about that. And they basically, if they can count the methyl groups, they can count the number of branches, because each one has a tag on it of a methyl group. So they measure here the number of branches, basically from these CH3 per 1,000 carbon. And since it's every 8, they can divide by 8 and figure out how many branches they have. Right, so in the C1, so the branches, adding the branches dilutes the methyl groups. There's a branch in every 8, but there's going to be dilution of the CH3 by the branch itself. When it's 10 long, it's going to dilute out the branches. So the 10 has the lowest CH per 1,000, CH3 per 1,000 carbon, because you're including the branch carbons too. Right. So in fact, this would be since it's 8 between and then 10 up here, that's going to be something like 50% less than the CH31, the C1. Right, so the C1 is something like 110, and 50% of that will be 55, and then the C10 is about 55. Right, so it works pretty analytically to count the number of. Then they're running this through a column, right? So you have a size exclusion chromatography column, which is going to be a gel, right, which has a bunch of pores in it on a nanoscale. So the molecules go in, and the small molecules will follow those pores around. So a small molecule is going to follow the pores through this meandering pathway. The flow rate is really slow, so there's a lot of this diffusion, this lateral diffusion. Right, so the small molecule is going to take forever to get through this maze, right? But the large molecules can't fit into the pores, so they just zip right through. So the big things just go ballistically straight through this. And the bigger they are, the more ballistic they are, meaning they go in a straight line. Right, so one of them is going to have a diffusion path. The other, depending on the size of the thing, the smaller it is, the more that porosity it explores, so the longer it takes to get out. So if you measure the time of coming out, you have some kind of a detector here, like an IR detector, or an index refraction detector, then you can say, like, you're going to have a distribution curve, and the low molecular weight things are the shortest time. So this is retention time, and then this is whatever signal, like index refraction, proportional to concentration, and then the short things are coming out first, and the big things are coming out last. Right, so you can take the stuff that comes out, it's in dilute solution once it comes out, and they can run that through different detectors. So they run it through an index to get the concentration. They can run it through IR, so they can get this. They can get the branch content as a function of molecular weight. So these are the molecular weight distributions here. These humps, right? So, and then the cross molecular weight is pretty constant. So it means the branching mechanism that they used is pretty good. Right, they're basically getting what they thought they were going to get from that octene metathesis polymerization, cyclic octene, and basically the numbers also match up with what you'd count. So everything here from the IR is good. It works out just the way they thought. So it's a pretty nice characterization for that. Then they measure the intrinsic. This is the IR pattern showing where they pick out the CH3 somewhere in this. I'm not sure where. Probably somewhere at the lower. It's like this group over here, I think. Right. So anyway, so then they run intrinsic. They get intrinsic viscosity on it, and they get these curves are all parallel. They're basically all parallel, right? So they get intrinsic viscosity for every molecular weight that's coming out of this chromatography column. Each one is monodispersed, right? So they can get, for each sample, they can get hundreds of intrinsics, and they're all different molecular weights, so they can get the Markovit coefficient from that. Log of this versus molecular weight gives this A. There's two parameters, A and K. So the intrinsic goes with the K and A is going to be A is going to be 3 by DF minus 1. Right. That's our Markovit thing. Right, so we're expecting like 0.8 for good solvent, and then 0.5 for theta solvent for this A. If that's working, right? Because it's 3/5, 5/3, so it's 9/5 minus 4/5 is 9/5 minus 5/5 is 4/5, and 4/5 times 2 is 8/10, so 0.8 for good solvent. And then it's 0.5 for theta because the F is 2, 1.5 minus 1 is 0.5. Right, so those are the powers that you expect, and they get something like 0.7 out of this, and they're all the same. So putting the branches on doesn't change the chain scaling, the fractal dimension. It just changes the density. So you have these chains, they're all the same. If they're the same molecular weight, they're all the same size, and some of them are going to have these branches, and some of the branches are short, and some of the branches are pretty long. Right, so the size of the thing stays the same, the mass goes up, That means intrinsic, which is the volume per mass. So the volume stays the same, the mass goes up, so the intrinsic drops. Right, so you can see linear polyethylene with no branches is the highest, and then C10 is the least. It's the bottom, and it goes in sequence. Right, so you can see that better when he divides the intrinsic of the branched one by the linear, and then you can see that this G prime is his branch divided by linear, and you can see that the 1 is here, the 2 is there, then it goes 4, 8, and 10. 4, 6, and 10. I mean, it's no 8, it's just 6 and 10. Right. So basically, this is supposed to be a measure of the branching, this G prime. I'll go through that a little bit later, but so anyway, so they get that, and then that's kind of the main thing that they got. And then the scaling is basically a good solvent for all of the things. The size doesn't change. So, but we saw, anyway, we can look at this a little bit later, the details of this, but so it's nice kind of little paper, about how to make controlled short chain branching in the polymers, right? So, and it seems to pan out okay, except that they miss a few points, which isn't, well, it's a pretty good paper. It's okay. So let's see if I can shrink that down a little bit there. So the quiz goes like, read the introduction and then explain the difference between SEC and HPLC. So there's another paper, this Chatterjee one that I was mentioning, right? Deep-root Chatterjee. So they're looking at different ways to do chromatography. So they have a nice kind of introduction for chromatography. And they mention like the difference between, so there's two types of chromatography that look exactly the same. So you have size exclusion chromatography, and then there's high pressure liquid chromatography. Okay, so SEC and HPLC. Right. So what's the difference between these things? Well, they're the same thing. They have a column. This will be what kind of look like a wire or something. It's usually in a temperature controlled thing. Then they're going to have a pump and some kind of an injection rig. So you have flow going through, and then you inject your sample into that flow. And then it's going to run through this column. Then it's going to come out, and there'll be a variety of detectors over here. There'll be like an IR. There's an index refraction. There's a viscosity detector. So that's going to have like a 2-channel setup where they can measure the solvent versus the solution at the same time under the same conditions. And then they can run this through light scattering. So you can just put a light scattering instrument here and get the intensity as a function of Q, which can give you the rate of gyration, and it can give you the second Vero coefficient, so chi, and it'll give you the molecular weight, the weight average molecular weight. But all the moments, since these are monodispersed fractions, every time it comes through, the weight average is the same as the number average, is the same as the viscosity average. To get viscosity average from viscosity, get weight average from light scattering. I think those are the only things they do, right? Light scattering and viscosity, right? But the molecular weights all agree, like they're all going to be exactly the same number. It doesn't matter which way you get it, right? But they can get rates of gyration here. Then from the viscosity, they can get the hydrodynamic radius from the intrinsic, right? That's going to be the hydrodynamic radius divided by cubed divided by molecular weight, right? So you can get hydrodynamic radius and radius of gyration out of this setup. So anyway, so the difference between SEC and HPLC, this one is basically looking at this random path thing. So that's basically like diffusion. So that's entropy. Notice how random is the motion of the particle. Is it ballistic, not random at all? So entropy is 0, or is it this big random path that entropy is some number, right? In the less the less that the particle searches out through the sample, the less entropic it is. So basically, size exclusion is an entropic measure. This high pressure liquid chromatography relies on, as the polymer is flowing through, it's having chemical interactions with whatever's in the column. So the things that have more chemical interaction go through slower, and it doesn't matter the molecular weight. Right, so liquid chromatography is enthalpic. It's like interactions. So you have these two kinds of chromatography that are basically the same, look like exactly the same. They are the same machine, but basically it's got an entropic part. An entropic part is this size exclusion characteristic. An enthalpic part is the liquid chromatography part. Right, so you could separate on both ends. Then also Chatterjee goes through a lot about something called TREF. TREF is temperature rising elution fractionation. So that's something that was invented in Cincinnati at Lyondell-Basell. So it's a technique where you take, and it's used basically for polyolefins, but you take the polymer, you put it through a column, and then usually for polyethylene, you use dichlorobenzene for solvent. Right, so you have benzene with 2 chlorines on it, and then basically it has to be run at 80 degrees C, or the stuff precipitates out. So in TREF, you let it precipitate out. So you run it through, and then you cool down the column to something like 50 degrees C, and the polymer all crystallizes on the column. And then you slowly raise the temperature back up towards 80 degrees C, and different things melt earlier. It's like the linear low densities will come off first, and the high density comes off last. Right, so that's the idea. You're going to go through a temperature. So you both have size exclusion, and you have fractionation according to the melting temperature. So you can look at the structure of the things that come out according to where they melt. So that's temperature rising elution fractionation. Another technique that this Chatterjee, actually this paper is a seminal paper for that in 2016. They introduce they have a high density polyethylene, and then they have some block copolymer that's got high density and some other thing like linear low mixture, right? Then they want to separate these two, but they actually have the same molecular weight and the same hydrodynamic radius, so they come out at the same time. But so in order to separate these two, they're flowing it through the column, and they put in a plug of a solvent that allows the block copolymer to flow through, but doesn't allow the high density to go through. And the solvent's going to move slower than the polymers because the solvent can explore all the porosity in this thing, whereas the polymers kind of zip through ballistically, right? So since this BCP can go through that plug, it zips right along and passes right through that without knowing and comes out. But the high density gets stuck behind the plug because it can't dissolve in it, and then it comes out later, right? So they're using that to separate these different kind of fractions of, they're using that to separate these fractions of high density. So they introduce this plug that blocks the high density, but lets the block copolymer go through. And then they use that to separate the fractions. So it's kind of interesting. She mentions that, and they mention that in this paper. Right, so there's a lot about chromatography here. I just thought you kind of look at that while we're looking at this paper. Then, so that's the first question, like just say something about chromatography. Then explain why this might be the case. So figure 3's main point is that the intrinsic drops with the length of the branches, right? So oops, how do I do that? That's not what that's supposed to do. Let's see. I think I just lost my, somehow I lost the program crashed out. It's down here somewhere. Like that hasn't happened before. Get this thing. I don't remember where it was. Apparently not. Oh, no, there it is. Got it. That's the wrong thing. This is the right thing, but not the right, not what I want right now. I just want this 12 quiz, right? So B is like explain why it's the case. So the case I said before, like you have the chains. So the chains are keeping the same hydrodynamic radius. So these these short chain branches aren't impacting the coil. So that means that basically there's no change in the Kuhn length. We saw like if you had brush polymers, the Kuhn length goes up, but those are spaced pretty close, right? Those are small spacing. So, but here you have a pretty long spacing between the branches. It's 8 carbons between them, and these branches are like 1 to 10. So apparently it's not enough to change the Kuhn length so that the hydrodynamic radius doesn't change. All it changes is the mass. So your hydrodynamic volume is the same, right? And all you're changing is the mass. So as the mass increases with more branching, with longer branches, and there's the same number of branches per chain. So as the mass increases, then then the viscosity drops. Then the intrinsic viscosity drops because the mass is increasing, so it just goes straight down. The slope stays the same, so the coils are the same scaling, the same hydrodynamic size. Right. So if you use that as a model, you could write an equation for this. You'd say intrinsic viscosity of short chain branches would be like the linear one. And then you're just talking about that the hydrodynamic volume is the same. So it's just a matter of calculating the mass ratio. So it's the mass ratio of the mass of the linear divided by the mass of the linear plus whatever the branches are adding. So the number of branches would be like the linear mass divided by 8 times the monomer mass, right? And then the mass of a branch is the number of carbons times the monomer mass. So if you look at that equation, so that's the total mass of a branch, and the top is the mass of a linear. Turns out everything's got mass of linear in it, so it cancels out. You don't need to know the mass of the linear. It doesn't matter, right? And then because you take 8 times the monomer and it's times the monomer, that also cancels out. So you just end up with the number of carbons in a branch divided by 8 decides this thing. So it's going to be the linear intrinsic divided by 1 plus the number of carbons in a branch divided by 8. Right, so it becomes like a pretty simple function. So you can calculate kind of how your intrinsic viscosity shifts with the increasing length of the branches. Right, so you have for the linear it's 1. And if you add 1, it drops because the mass is increased. And if you add 2, it drops a little bit more. If you add 3, it drops. If you add 4, it drops even more. If you add 6, it drops more. And if you have 10, it drops the most. Right, so you get down to 0.444. So one way to look at that would be to say if you have the intrinsic viscosity versus molecular weight, so you're going to have these lines. So they have a slope of a. So you have m to the a times k is the intrinsic. So you could say, well, a is about the same for all these. So I can just take the k's. And that would be the intercept over here, 0 molecular weight. But basically should go with this shifting of the intrinsic viscosity. So if you do that, you get these numbers which bounce all over the place. So he's got this table of it's table 1. He shows this k values and a values right here. So here's the a values. So the a values aren't the same. That's one thing. They shift over. There's some error. And then the k values are here, right? So you can take the ratios of those k values and get something that doesn't look too good. It doesn't match up with this prediction. But if you go to the G prime, the branching plot, which is a ratio of just the ratio of the 2 intrinsic viscosities, this looks a lot better. So here you can put I want to expand that. It's not really doing it. In fact, it just went nutty. So it'll come back. But so you can extrapolate what these numbers are from this plot. oh, there it did it. So, right, so you can get a pretty good idea what the values are here. And they're almost exactly the same as the predicted, this kind of equation, simple equation. So it's 0.88, 0.84, 0.8, 0.7, 0.66, 0.65. They're almost the same number. Some are exactly the same. So I mean, that works pretty well as a model for what's going on here. They didn't do that in the paper. They probably should have, you know, but anyway, so that's part B. Then the question is, so we know from the simulations that branch chains that the Kuhn length is one of the main things that changes. So what about that? Like, where is that in this thing? So so basically, they didn't look at Kuhn length at all, even though that's in the literature, right? So they missed that completely. It's in experimental, also in simulations, right? But so they completely missed that. So does the Kuhn length? So basically, the Kuhn length would impact this stuff, right? So it would impact all these things except molecular weight, right? Molecular weight's shifting because of the branch mass, but basically all these features are going to be changed with the Kuhn length. Intrinsic changes. So if you say at the extreme you had the Kuhn length became the entire chain and it just became a rod, well, that's going to have quite a bit different intrinsic viscosity than coil. The hydrodynamic radius would be different than for a coil. The radius gyration would be a lot larger for a rod than for a coil, and the C star would be different. Right, so everything gets impacted by the Kuhn length, which they completely ignored in this paper. So that's one feature that's missing. And then there's this correction factor, right? So so the correction factor. So before explain what it is. So it's supposed to be used for G prime is supposed to be used to look at long chain branching, not short chain branching, for one thing. So let's see. So this is from this book by Utraki and Jameson. It's just going through this G factor, right? This branching parameter. So this is this one for radius gyration, there's one for viscosity, right? And basically, they've related it to the functionality, like the number of long chain branches in the system. So usually this G is used to talk about long chain branches, not short. So this is kind of what it is. You know, it's not something to use with short chain branching, but nonetheless they used it. Yes, it's a little odd that they talked about it. And this is showing kind of with the number of long chain branches that this GN drops, right? And the dashed line is this functionality. So or G viscosity. So it isn't exactly appropriate to use this G for it's useful for us because we got this predicted value. Basically, it's not intended to be used for and if you said, like, what is it for 0.6, you would go back to this long chain branching function and say, when does that equal 0.6? And it equals it when you have 8 long chain branches, or 7 or 8 long chain branches in the chain. Right, so there's functionalities that predict what that G is. So that's that business. And then they show, there's one other feature here that they show, which is that this purple is a C6 and then green is C10. So when you get to high molecular weight and the fractions, this thing isn't power law anymore, it tails over. Okay, that means, since this is 1 over density, and then the intrinsic is below your expectation, that means the density is higher, which means that you're getting long chain branching. That's kind of what this is a signature of. If you look at their supporting information for this paper, at the end of it, they show a better example of this. So you can see here that these things tail over quite a bit. So it's a C4 tailing over, green is C10 tailing over. So that's because they're getting this long chain branching because when they are hydrogenating the double bonds, or when they're putting it through this high temperature pressure hydrogenation, they're making some free radicals, and then those are bonding up to make branches, long chain branches that are showing up in the intrinsic viscosity that way. You can see that. Let's see this. There's a picture of that somewhere here. So here, this is high density polyethylene. This is low density. It's got a lot of long chain branches in it. So you can see that the two are the same at low molecular weight, but then it tails over when you get more and more branches. The larger the chain, the more branches. So that's kind of standard behavior for low density, for kind of like high long chain branching. You can see that tail over because the chains get denser. So this is 1 over density. This drops compared to the expected value. And this is a dendrimer. You see this thing is like a U-shaped thing. So basically that's it for the quiz. If you have any questions, email me about it. So I want to kind of move on a little bit here. So we'll get rid of this thing. So you don't need this. I'm going to just go over here to talk a little bit about just talk about the this branching idea, right? So we have this issue. So we know that the intrinsic only depends on the density, right? So the density doesn't really have to do with the branching, right? Not directly. It's basically this fractal dimension that you get from the intrinsic viscosity isn't going to help you much with talking about what the structure is of this thing. Right? So you basically need something else. One way to look at it is to take something like this picture of a branch structure, right? So how's this going to pan out? So you have the entire object, which has a mass Z, right? And then you can say that so for the entire object, you have some size R, then you have a mass Z, and the density of that is going to be the mass. So it's going to be Z divided by R cubed, right? And then you know that R goes with the mass to the 1 by dF. So this thing will be Z to the 1 minus 3 by dF. Right? So if you know the mass of it, and you know the fractal dimension, you get the density. So the fractal dimension gives you the density. That's what it gives you. Right? So density isn't going to tell you. It won't tell you. Say if you have a disk, then the fractal dimension is 2. If you have a coil, the dimension's 2. So there's no distinguishing feature between those two. So you can't tell what anything is. It's just telling you the density. If the thing spins in space freely, right? So then what can you break apart out of this thing to get the structure instead of the density? Right? So you can use the same approach, but instead of taking the total object Z, just put an electric current through it and find this path, the black path. Right? So it's called the minimum path. It's a short circuit path through the object. Right? So that short circuit path you can break apart into another object, right? So you can just take that alone. Now that itself would have a fractal dimension. It's got the same size R as a coil, as a branch structure, but it's got a different mass. And its mass is this minimum path P, and then the dimension of that thing is D min. So it's 1 over D min, minimum dimension. It's going to be a lower number than the fractal dimension. So you have the fractal dimension, and this D min has to be lower than it. Right, so that's kind of one thing. So, but if you want to take that number P, it's related to the number Z, the total mass, by this dimension C, which has to do with how it's put together, like how the branches are. The bigger the C is 1, then it's a linear chain. If C goes up, it becomes branched, but C also has to be less than or equal to DF. And it turns out that the DF equals the convolution. So d min tells you the convolution of a short circuit path times c, which is how branched the thing is. So through these two dimensions, you can explain the structure of the thing and the density. Right, so that's kind of the idea, like that you would want to talk about both of these things. Right, so convolution and topology gives you density. That's the idea. So since you have R equals P to the 1 by D min, and you have R equals Z to the 1 by DF, there's another thing, R equals S to the 1 by C. And what S is if you took this object and just took the topological points and drew straight lines, so D min is 1, then you would have like a stick figure of the object, and that the mass of that stick figure would be S. Right? So that gives you R to the C gives you S, R to the D min gives you, R to the DF gives you Z, and R to the D min gives you P. Right? So this is topology, this is convolution, and this is density. Right? So you can break apart the structure into that, and with that you can tell what it is. Right? So for instance, like if you have a disk, then the short circuit path is a straight line, so D min is 1. If you have a coil, the short circuit path is 2 because it's the same as a chain dimension. And the topology C, it's linear for a coil, and for disk it's for disk C is 2 because it's a two-dimensional object. Right, and those two will both give you 2 if you multiply them. So that both DF is 2, 2. Right, so that's kind of how this works. You can use that in the context of this intrinsic viscosity, and you'll find out that basically say you took the RG like this definition of G, which is RG squared. That's the original definition. You just find out that you just get the fractal dimension, you just get the density difference. So you don't get, from the hydrodynamic radius, you don't get the topology from it. You're just getting the density. Right, so this intrinsic thing is not going to tell you what the thing is. It just tells you one thing's denser than the other thing. It's not telling you anything about what it is, what the structure actually is. So we already talked about polyelectrolytes sufficiently. All right, so then that's the end of the intrinsic viscosity stuff. So I buried that. That's good. If you have questions, email me and I can answer it. So I wanted to go on. This is dynamic light scattering. I want to talk about that a little bit, like kind of briefly. So basically, this is going to involve correlation functions, right? Which is something that is used in a lot of different areas. Right? So for instance, like, so if you take a structure, say you take a crystal, and then if you go across the crystal like this, you find out that you have plot the density versus position, and you have kind of spikes where the atoms are. Right? So that's density is a function of position. So one thing, a statistical way to look at this is to say, if I take a point, any point here where I'm in a phase, I'm in one of the spikes, and I go out a distance r, right, and then I see another spike, right? But if I go a shorter distance, I don't see it. So I take this point times that point. So I take the density at 0 and the density at r, and multiply the two together. Then I can sum those up. Right? Then I get this. That's a correlation function. As long as I sum over all starting r's. So it's like the density at 2 points separated by distance r is going to be this g of r, this binary correlation function. right? And for this case, it's going to just look like almost like the same thing as the density. So if you're at 0, you're always on the spikes. You always have G of R is 1 always at the start. Right, and then there's some kind of usually smeared outness to this, so it'll drop down with an exponential, and you'll go along, and then there's the other atom, right? So it'll be like that for a crystal. It'll just keep going. But if the thing, say the thing's a liquid, right? So there's atoms kind of floating around, and you have excluded volume, so that there's kind of a closest partner pair here. So you'll have basically that for a liquid, this thing's going to be an exponential decay. It'll be like this, e to the minus r over some correlation length. Right. So this is something that, so it turns out the Fourier transform of that gives you the intensity, the scattered intensity, I of Q. Fourier transform of G of R gives I of Q. So they're related by this Fourier pairs. Okay, so this is used in, it's kind of interesting, it's used in analyzing mixing for polymers. Like when you put a pigment in, and then you want to see how well it's dispersed. So the top one shows, this shows just different ways to disperse things. So the left thing is a random distribution. So you can see there's some clusters in it, the dark spots, and there's a lot of holes, and there's different densities through this thing. And the right one is where you have a preferred distance. Okay, so looking at this, you couldn't tell. If you do the correlation function of the one on the right, so if you do G of R on that one on the right, it's going to look like this. So it'll be at 0, at R0, it's 1. And then it's going to have some decay down, and then you'll see that it's got a preferred distance. Because the way these things are spaced, they're spaced at a preferred distance apart. Right, so it'll have a spike, and then you'll have a weaker preferred distance out further. Right. Whereas the one that's random, so the one to the left, G of R is going to look like just a decay, like that, an exponential e to the minus R by some length. This would be like the correlation length. Right, so things look, so you wouldn't be able to pick out this peak if you just look at this thing. So this could be happen if these things are charged. They'd have a repulsion, so they wouldn't be able to approach each other, and they would have this kind of distribution, which has its preferred distance. Right, and then this is the case where they're actually really random, which isn't a good mixing. It isn't exactly a perfect mixing. Right, so the first order, he's talking about mixing, but the first order means just the density of, so how much white, how much black is in this, and they're the same. Both of these pairs have the same density, but this has to do with random versus actually preferred distance. And this left one is also random, and this one has a coarse grain. So there's a grain coarseness. It doesn't have to do with the first order distribution, like the mass distribution. Right, so there's different kinds of mixing. These are from this book, Tadmore and Gugas, Polymer Processing. It's on the webpage, but if you want to look at it, this is typical for polymer mixing. So you put carbon black into low density, and then you get these streaks. And you say, well, there's a gradation across this. They're doing a different extrusion rates and temperatures. You can see there's a gradation of mixing. So this is kind of a map by Tadmore of how to do that. So you have two kinds of mixing, right? One is a diffusional mixing, right, where the boldness of the phases decreases until you get perfectly mixed up here, the top left. And the other is the decreasing scale of segregation. So you're breaking up the pieces, and that would be caused by shear strength, right? So if you take the correlation function, which takes the intensity of the material at two positions separated by a distance r, right, multiplies by each other and goes through all the possible pairs, and that's normalized by the standard deviation of that, which is this number over here. So you get that R of R, and then if you integrate that, you get this scale of segregation, like how big are the domains of this thing. Right, so this correlation function is related to the scale of segregation if you integrate it. This business about reversible shear strain, this is reversible, and this diffusion isn't. So anytime you have a gradient, something's not reversible. Anytime you, so the shear strain though is reversible if it's laminar flow, right? And that can be demonstrated. This is something kind of interesting to look at here. Oops. That's what I want to do. Just show this to you. Oh, actually, this is already open. That's okay. This will show this. So they're doing laminar flow, and this is showing that it's reversible. So they put some food color into glycerol, or it might be just corn syrup. And then they do laminar flow. So they have a Couette viscometer. So they have, it's a cylindrical chamber, right? And then he reverses it, right? So it's not reversing the video. This is actually physically reversing it. Then you end up with exactly the same thing. So it's almost completely reversible, except for the diffusion that happened in the thing. So let's see. So this is the before and after of that. So you can see that some diffusion happens. So it did, in other words, the thing about losing the dark and the thing diffusing out, that's diffusion. But as far as the breaking apart the streams, that's a reversible feature. So laminar flow is reversible. That kind of demonstrates it. So basically, that's just got to do with this mixing. But the scale of segregation basically has to do with this dispersive mixing idea in these systems, right? So anyway, the only reason to talk about that is because this is just showing for different kind of what a correlation function looks like, right? For this is in space. So you can also do a correlation function in time. So say you have a time-dependent pattern like this, right? It looks like it's noise, but actually this thing's made up of a bunch of sine waves. So this is shown just because it's an example, a model system that's made up of sine waves. So you can see here, it's a dampened sine correlation function. See, this is what the use of correlation functions. It takes a noise pattern, what looks like a noise pattern, and breaks it into things that are recognizable. Right, so you can see there's a frequency to it, and then there's amplitudes. So basically, this isn't a noise pattern at all. It's basically a sine wave correlation function, similar to the thing where we looked at these mixing situations. And we had the two mixing things, like these things. So this looks like it's random, but it isn't random. That's got correlations in it. Right. So anyway, so in dynamic light scattering, you use a correlation function, the same kind of thing. So you're gonna shoot a laser beam at a sample and pick up at some angle, right? And then we have that angle related to some size scale. So we have at that angle, we have Q is 2 pi over some size d. Okay, so we have some size scale associated. So we're taking the material which has things in it, and we're throwing in a rod of size d or size r, say, change d to r. So then we're just kind of randomly putting that into the system because these things are moving around with KT all the time, right? So we're measuring the size r time correlation of these particles. Sometimes they'll be together, and the two ends will give a scattering event, and sometimes it'll be just one, sometimes it's nothing. Right, so those two don't give a scattering event. It has to be a particle on each end of the vector r gives a scattering event. Right, so since these things are moving, the probability of that happening changes with time. So it's going to be that kind of noise pattern like that. Right, and then you want to take every possible point in time, separated by a distance, delta time, and then vary that delta time in order to get this time correlation function. Right, and that thing is going to relate to, I'm using these notes which are on the web page in the book section by this guy, Paul Russo. was at LSU, and now he's at Georgia Tech. So gotta put his picture in there. Anyway, so this is the time correlation function. So we have like a time t prime and then time t prime plus t, and this is going to be the correlation function as a function of t, the separation distance in time between the two intensities. And then we can get that, and then that thing is going to be related basically to an exponential decay. And the argument of the exponential decay is going to be the diffusion coefficient. And the diffusion coefficient by the Stokes-Einstein equation is going to be kT divided by 6 pi times the hydrodynamic radius times the viscosity of the solvent. So you get the hydrodynamic radius from this decay in that correlation function. Right? And it's not under a shear field. Right? So this is going to be a quasi-stat, just diffusion of the particles through the system. So there's no field on it. It's just moving around. Right, so this is a better hydrodynamic radius than the thing you get from intrinsic viscosity, and it's kind of faster to get. Like this thing is pretty easy to do. So I'll talk about this a little bit more next time. Like I'll just go straight through dynamic light scattering next time for Wednesday. So if you have any questions, email me. Okay, and then I'll have another recorded lecture for Wednesday. Yeah, thanks.